evolving, and then one with everything else evolving. So that everything else is solar variability, ozone, volcanoes, land use, land cover change. So this allows you to look at additivity because all of the forcings are evolving in one of these simulations. Motivated by the work that was done for the description paper, we've also run a secondary ensemble, which was run in the same way as CESM1, where everything is evolving except the aerosol forcing, and the aerosol forcing is kept fixed at 1920s values. So we just revised the paper, had minor revisions, so hopefully the description paper will be out soon. And so now we'll just give a quick run through of the kind of future simulations that are either started or about to start or will be going on in the coming year. So there's a couple of offshoots from the single forcing large ensembles. So motivated by the fact that we do see a pretty big method dependence on the aerosol influence on global mean temperature in CSM2, which you can see here. So the solid is where only the aerosols are evolving, and the dashed is where everything but the aerosols are evolving. And the maroon is CSM2, and you see this big method dependence in CSM2 that wasn't really there in CSM1, where you compare the teal lines. But we have pretty big differences in the forcings that were used between CSM2 and CSM1. So we are going to run some complementary ensembles where where CMIP5 aerosol forcing is being prescribed. So we can see, is that having different forcing really key to having this different method dependency? Although there are arguments to be made for why the models are also different and contributing to that. Another one is motivated by, again, some of the results with the single forcing large ensemble. So if you look at the green line here, this is the everything else ensemble. And in the early 21st century and the late 20th century, you can see that it's warmer than it was compared to 1920 to 1940. So we're kind of interested in what is producing that warming. And I think the most likely candidate is the volcanoes as you transition from the historical period where you have all these kind of intermittent large volcanic eruptions and you go into the SSP where you just have kind of some background aerosol. Is that what's giving rise to this warming? So we are going to run a separate set of members that have only the volcanoes evolving in time. There are ongoing simulations with the next generation grid of CAM. So CAM is moving to a higher top, 80-kilometer top, and a higher vertical resolution. So here you're seeing the grid spacing. So this is the difference between each levels as a function of height. Red is the new grid, so we go to a 500-meter grid spacing, and we go to a much higher height. And one of the motivations for going to this new grid is that we now start to represent the quasi-biennial oscillation. So there are going to be many changes in CAM7 compared to CAM6, but as part of the working group allocation, what we've done is to look into kind of the intermediate step of how does changing only the vertical resolution impact on the simulation. The next generation will also have enhanced resolution in the boundary layer. We're not changing that because when you change that, you have to start retuning. So we have a 100-year-long pre-industrial control, and then there will be 3 coupled historical into SSP 370 simulations, which can be compared with the large ensemble. There are some AMIP simulations, and Yaga and Nan are also running some nudged QBO simulations for part of the QBO intercomparison project. So these data will hopefully be available sometime later this year. There also is a motivation to run these simulations because there's a big project going on with Scripps where they're using this model configuration for S2S predictability ensemble, which we may hear about more tomorrow at the Earth System Prediction Working Group. There's regionally refined North Atlantic simulations going on. So this is a grid that was generated by Rob, who's here, and Adam. And it's going down to a 1/8 degree resolution in the North Atlantic. And so we're running a 1958 to present day AMIP simulation with this grid with the motivation of seeing how does having that kind of unprecedentedly high resolution in the Atlantic for this long of a period impact on ocean-atmosphere coupling and the North Atlantic jet stream variability. This is a project that is being led by Flavio Lehner. So he is interested in we have had one kind of realization of the force response plus the internal variability that we've looked at in the real world, but there are many other ways that internal variability could have gone. So this is using kind of synthetically generated histories of sea surface temperatures using a linear inverse model to sample what could have been in the past, and taking kind of extreme members, ones that give you more of a warming in the tropical Pacific and ones that give you more of a cooling in the tropical Pacific, to see what the impacts of those different kind of outcomes of variability would be, particularly on North American hydroclimate. So those are underway, and we'll probably make those available when Flavio has written his paper about these. Okay, a couple of other projects that are ongoing. Brian Medeiros is running a regionally refined tropics simulation with 1/8 degree in the tropics to look at the impact of having that resolution on tropical variability. And we'll soon start an SSP 585 medium ensemble. The plan here is to have 15 members, and so once we have that, we'll have kind of a reasonably large ensemble size for each of these different scenarios. And I guess SSP 585, while people maybe think it's not really something that's going to happen at this point, it's kind of useful for comparing with the RCP 8.5 that was used in the CSM1 large ensemble. Okay, so we have a couple of minutes. I'll hand this back to Aishu to explain these ones.
This is the tropical basin interaction quantity experiment. For this experiment, we have two sets. One is historical pacemaker simulation, which we need to run 10 ensemble members from 1850 to at least 2021. And after 2014, we will use SSP 585 forcing. After that control simulation, we have three sets of pacemaker simulation. It's Pacific, Atlantic, and Indian Ocean separately. Each we run 10 ensemble members. For the SST, the SST will be relaxed to observation for the full field between 10 degrees north and 10 degrees south. And the transition zone is 10 to 30 south and 10 to 30 north. And this will be run under CVCWG working group allocation. The other side of the simulation is we call pacemaker handcuffs experiment. For this experiment, first we need to get a new condition by relax the global SST and SSS to observations and run the period 1982 to 2021. After that, we will run a set of a pacemaker simulation for the global, and then it's Pacific, Atlantic, and Indian Ocean. Each of these simulations will start. We have 4 actually starting months: February 1st, May 1st, August 1st, and November 1st. Each of these simulations will run for 12 months. And the February 1st, that one is required for every group to do. And for others, it's way better to do it, but not required to participate in this project.
Okay, thanks. And then Sarah.
Yeah, I'll try to make it quick so we don't get too off on time. So one of the things that Kay found when we ran the historical run for this mechanically decoupled configuration was that when we don't allow external forcing to drive changes in the ocean circulation, that the model doesn't warm as much. And so naturally, one of our questions was sort of what's the role of aerosols versus greenhouse gases. And so we're going to run a 10-member ensemble with just a greenhouse gas only over the historical period. And then the other kind of major questions that we've gotten in the past, particularly at the pattern effect workshop, was it's hard to compare the historical runs to all the climate sensitivity runs. So we plan to do a 1% CO2 simulation and a 4 times CO2 simulation, so we can kind of apples to apples compare to the fully coupled version. And those should be run this summer.
Great. I think that's all we have. I guess we're a little behind time, so we do have, well, maybe we have some time at the very end of the day. So I guess if you have questions, maybe try and remember them, and we can have a bit of a discussion about any of these things or any other things you'd like to see the working group do. So I guess we'll get started then with the talks. So I think, is it Carlos, are you first? Yep. Yes, okay. So our first speaker is Carlos Martinez. What am I, do I enter full screen? Okay, all right.
Great.
Oh, I should go, maybe you can take this one and I can.
Here you go. Postdoc on my second year, and I'm going to be talking about Okay, I'll just do this because it's just easier. Hi, everybody online. Just a second. Okay, I'll just leave that there. So the Caribbean. So many stakeholders rely on rainfall for their socioeconomic needs, and that's why climate and weather services rely on information regarding rainfall, especially given the projected changes to the cycle, as well as the hydrometeorological disasters that have affected the region that have exacerbated the concurrent socioeconomic issues in the region. So from this, I was really intrigued into investigating this region. I'm also born in Puerto Rico. I have family there as well, so there's a personal antidote. And when I looked at the literature, I found numerous dynamical mechanisms that many studies picked one or two that influence the rainfall cycle. And so I'll break this down bit by bit to show from my study, Martinez et al. 2019, what these mechanisms are when I developed a more comprehensive understanding of the mean state of the cycle. So we'll start with the large-scale features, the first being the Intertropical Convergence Zone, or the ITCZ. That is a band of moisture convergence that moves north-south with the solar insolation cycle by a lag of 1 to 2 months. Then you have the North Atlantic Subtropical High, with it the easterly trade winds, which is a main facilitator of moisture convergence across the Caribbean basin. Then you have some regional modifiers. One is the Atlantic Warm Pool, warm body of ocean water at 28.5 degrees centigrade or above, that expands or contracts with the solar insolation cycle. Then you have the Caribbean low-level jet at 925 millibars that in its exit region enhances zonal convergence over Central America and enhances divergence on its entrance region. And then finally, you have some transient features, which I found in my study to be marginal impact on the mean state of the rainfall cycle. Those can be the easterly waves that move from West Africa and can develop tropical cyclones, as well as cold fronts from the mid-latitudes that can influence parts of the Caribbean basin. So as you can see, there's a lot of features, including the localized forcings like sea breezes as well. And I was able to find that the two main features, the ITCZ and Nash, are the main contributors for moisture across the basin. And then you have some modifiers and then some transient activity that have a marginal impact in the region. So from this refined understanding, with more information, you can look at that previous paper to see how that plays throughout the seasons of the rainfall cycle. I wanted to look into modeling, given that modeling studies have not looked at or explored to the extent that I found in the observed hydroclimate, those governing mechanisms that impact the Caribbean region, and look at it on a sub-regional lens as well as a seasonal lens. And so these are several of my objectives. First is to look at what global circulation models or GCMs simulate the cycle and the mechanisms that govern it. Do models perform better, for example, over ocean-only grid spaces where you have less complexity, such as land and those land interactions that you have? Are there biases specific to the entire basin or specific to a sub-region of the Caribbean? And then is there a relationship between, for example, model resolution and precipitation estimates, or the configuration of the model, such as when you prescribe SSTs and what we find in those precip values? So what I did was I spent a lot of time collecting a lot of data. As you see on your right are all of the models that I collected, including the members that were used, their atmospheric model. I also have their ocean model. I just haven't, I don't have it described here. In the atmospheric model used, including their resolution. The first top right section, that is the CESM, the Community Earth System Model Group, including the version 1 and 2 lens and the GOGA runs or the SST prescribed runs. And then I also have the high resolution CESM run, which runs under a 25-kilometer grid under the atmosphere model in a 0.1 degree grid in the ocean, which allows me to assess the value of a higher resolution CESM versus the 1 degree approximate grids from the other runs. And then I also looked at what's known as the CMIP6 high-res MIP project, which allows me to better assess having a model with just differences in resolution between their low and high resolution versions. So they're the exact same model, just differences in that. And then I looked at several observational data sets, including several rain gauge data sets from the Caribbean Institute of Meteorology and Hydrology, and several satellite or blended data sets to have a robust observational benchmark to compare with the models. Okay, so with that, the first part that I'm presenting is looking at the Caribbean hydroclimate between observations and models. For this section and for the entirety of the presentation, I'll be showing just one seasonal component of the rainfall cycle, known as the early rainy season, which is from April through June. That is the growing season. And what we see here is a box whisker plot showing an example of one of the subregions, or the Central Caribbean, which is over Puerto Rico and the northern part of the Virgin Islands in the Eastern Caribbean. And what we have are several of the different model groups, including the fully coupled runs and then the AMIP versions as well. And what we see is that many of the fully coupled runs, including the individual members shown in the dots, have values that are below what we see in the observational spread, whereas in the AMIP runs, we have values that are closer to what we see with the observations for, at least in this instance, precipitation totals during the early rainy season. When I examine the CMIP6 runs and expand into the different model groups, that's what's shown in the second row, what we see is this difference between low resolution versus high resolution versions, or looking between the blues and the reds, and then also a difference between the circles and squares, or the fully couples, and the AMIP versions, where again we see a similar result where we see the AMIP runs showing values closer to the observations than we find in the fully coupled runs. And then lastly, these two pink dots, which I didn't share earlier, that's the high resolution CESM, which both its fully and AMIP versions show values that are similar to what the observations show. So from this, I looked at a time series because I was really curious to see how the fully coupled and AMIP how these fully coupled and AMIP versions, their ensemble means look in this example for land-only precipitation totals in the Central Caribbean. And this is why I want to show the early rainy season, because I find such interesting results in this season versus some of the other seasons. For example, in this red box, it's very clear that the fully coupled runs show for many models in their ensemble means, they don't even show an early rainy season, such as the CESM runs, for example, versus the high resolution run, and a difference between the low and the high resolution versions of CMIP6, noting their standard errors in the shading. And the black dots, the black dotted lines showing the observations. When we look at the AMIP version, however, despite their coarse resolutions, we see a much appears to be a much better look of the early rainy season and the structure and the seasonality of the cycle. And so I found that to be really interesting. When we are prescribing those SSTs in the models, they do perform better overall. And so lastly, in this section, I wanted to show scatter plots of the rainfall cycle to better examine the individual models and what their values show between land-only precipitation totals in the y-axis and ocean-only precipitation totals in the x-axis. In the top row, we have the Central Caribbean between the fully coupled and AMIP versions, and then this is another subregion, the Western Caribbean, which is over Central America. And what we see is a very clear shift between the fully coupled and AMIP versions in comparison to what the observations are showing. And we see this consistently across the subregions when I am looking at this. We do see this similarly said for the ocean, where again, we don't have as much complexity as land, and for all of the seasonal components of the cycle. So when we shift to the dynamics, so what I did was I took correlation coefficients between each of the models' value of a variety of dynamical mechanisms, in this case, sea level pressure, zonal winds, and meridional low-level winds. And I compared that with precipitation totals in the Central Caribbean in this case. What we do see are these intriguing inter-model differences in the mean state, where we have, for example, in the fully coupled runs, a large low circulation over the Caribbean basin, accompanied by a circulation pattern that would imply a weakening of the North Atlantic subtropical high, as you would have anomalous westerlies where the easterlies are and anomalous southerlies, which would weaken the easterlies or shift the easterlies to a southeasterly component, thus producing more moisture being fluxed into the Caribbean basin and thus precipitation. Interestingly, in the AMIP versions, when you're even prescribing the SSTs, we still see a similar setup, which highlights these intermodal differences even in the SST prescribed runs as well. And so when I took a closer look, for example, I took a spatial average over the Caribbean basin, and I looked at what each model's ensemble mean value was for sea level pressure versus their Central Caribbean precipitation totals for the month of May. You do see this very clear relationship where models that have less precipitation than what the observations are showing, you also have higher pressure over that spatial domain. And in the AMIP versions, although the range is much smaller, we still see this intermodal difference, and to an extent, a difference between the reds and blues, or the low and the high resolutions. And then lastly, when I looked at other intermodal differences, thinking that, there could be something here with Nash, I calculated the center of the North Atlantic subtropical high in those fully coupled and AMIP runs, and I'm just sharing here what the fully coupled runs are showing, which is that most models have the center of the high further west or closer to the Caribbean basin, which highlights and may explain the enhanced subsidence and thus have a connection with the dry early rainy season bias that we see in those fully coupled models. And finally, when looking at June SSTs in those runs, we do see a very clear relationship in that most models have cooler SSTs, denoting also less precipitation in the region. And again, these findings are very similar across the other subregions in my analysis. And so lastly, this is the total moisture budget analysis that I computed looking at AMIP minus fully coupled runs. And what we see is that the AMIP runs, which, again, they highlight and show closer values to the observational spread in both the dynamics and precipitation. What we see is more moisture being flexed into the Caribbean basin, which again, you have anomalous southeasterlies versus what we see in the fully coupled runs, and what appears to be a low cyclonic circulation that's very similar to what I found in those intermodal differences when I'm, at least in this case, comparing the AMIP versus fully coupled runs. When we look at, for example, the high resolution CESM, we actually see the values, those anomalies, quite muted. And that's again reflecting how the AMIP and the fully coupled configuration of the high resolution CESM are quite similar to one another. And so the fully coupled run in HRC ESM does a fairly well job. And similarly to some extent with the CMIP 6 runs. And so in conclusion, I found most fully coupled runs underestimate early rainy season land and ocean precip totals across the region. I do also see those fully coupled runs also showing a stronger and westward shift of the Nash, which may cause those enhanced easterlies and divergence over the basin in those fully coupled runs. There is improvement in precipitation and large-scale dynamics when the SSTs are prescribed into the model, which may hint at the importance of SSTs in the region when characterizing the mean state rainfall. And then in several cases, I did find the high resolution estimate being closer, as well as those dynamical variables, than what I see in their low resolution counterparts. And I didn't share the other seasons, the midsummer drought and late rainy seasons, but I do find similar findings as well. And that's it. Happy to answer any questions. Thank you.
Thank you. Are there any questions? Yep, Dylan?
Nice talk, Carlos. I was interested to see the improvement in the precipitation with SSTs, but I was looking for a map of SSTs, a regression map of SSTs. I'm just wondering if there's a role for remote teleconnections to that region, other than just local SSTs.
Yeah, no, that's a fair question, and I didn't include that in here, but I do have those. And then here you kind of see the relationship in the SST, which are those contours, which I didn't mention, but you do find an influence in the Eastern Pacific as well. Most of what I found was localized, specifically with the tropical North Atlantic SST anomalies and what we see in the Eastern Pacific basins. Yeah.
Thanks.
Mm-hmm.
If anyone online has a question, feel free to raise your hand or post in the chat. Yep, Laurent?
We looked at the RSMIP ensemble for global precipitation and extremes in the Bado et al. Paper, I think, and we didn't find the same thing as you here, that the high resolution was necessarily better than the low resolution. So I'm interested to understand why in this particular region you would find this improvement, while on other regions, tropical regions in particular, we could not even. I mean, of course, there were more precipitation in the HR versus the LR, but it was not necessarily closer to the observations, given also that the observations have a very large spread. So.
Right. No, that's a very fair point. And the highlight that I have here is that in several cases, not all cases, we do see this. For example, the high resolution CESM versus what we see in the CESM lens runs. Specifically in the Caribbean, because you're dealing with islands in particular, you're going to have most likely, and what I do see in many cases is that these high resolution versions are able to see those localized features more, perhaps, and thus you're able to characterize those precipitation totals better than what you would find in a more coarse model. But that's not always the case, and I also show here that there are other factors at play, such as the large-scale dynamics, where you do see even in high-resolution models, they do not show the large-scale dynamics correctly, which does have an overarching role in the hydroclimate, given what I see in the mean flux and convergence, where you do see Nash and the ITCZ as the dominating modes for mean state rainfall. So it's a combination. Mm-hmm.
There's a question online. I guess while you answer this, maybe you could read it out. I'll get Rob's slide.
Okay, yeah. It says, "Hi, Carlos. Nice talk. Thank you. It doesn't seem like very much improvement in the precipitation simulations, even since CMIPS 3. Yes. Are the coupled simulation SSTs still 1 to 2 degrees colder than observed?" I would go back to look at my slides, but I don't have them with me. Yeah, the range would be about 1 degree. I would say the high resolution CESM actually fared the best out of the other model groups, where you had SST in the fully coupled about 0.25. Versus what we see in the other runs. But I do agree, the CMIP3, looking at Martin and Schumacher, which looked at CMIP3, you find a very similar result with the AMIPs improving. So it is consistent.
Thank you.
Thank you.
All right. Okay. Our next speaker is Rob Wills. Do you want to check that mic as well?
Can you hear me online okay?
Well, no, I mean, when we ask questions in the room, can they hear us ambiently?
I think there's those ceiling mics that they're turned on.
Okay, cool. Just making sure.
They go from red to green. I guess we should wait to see it.
Cool.
Did anyone respond about being able to hear me online? Okay, thumbs up there.
Oh.
Wait, someone said no?
Okay, yeah. Okay, no, it's fine now.
It's fine, okay now. Okay. Okay. Yeah, so I'm going to tell you about some new variable resolution simulations with CAM SE, CAM 6, and show some science results and show that resolving weather fronts seems to increase the large-scale circulation response to Gulf Stream SST anomalies. So compared to the simulation that Isla mentioned with high-resolution SSTs and an AMIP simulation, I'm going to be looking at some SST anomaly experiments that are fairly idealized. And so this is work in collaboration with Adam Harrington and Isla and also David Battisti at the University of Washington. So some motivation for this is the apparent underestimation of multidecadal variability in atmospheric circulation in mid-latitudes in coupled models compared to observations. So this is taken from a paper by Isla showing a comparison of the lens multidecadal variability in lower tropospheric zonal winds compared to the reanalysis multidecadal variability in the same quantity in DGFM. And this can also be found in other variables where you have quite a bit less multidecadal variability in these zonal winds in the models compared to observations or reanalysis. And there's also an apparent link of this, the winds in this region to SST variability. So if you regress the winds coming into like the UK there onto, I guess I can use the pointer like this. If you regress SSTs onto that, you find this SST pattern that is associated with these zonal wind anomalies. So suggesting maybe that these SST anomalies are helping to force this these zonal wind, this multidecadal variability in the zonal winds that's not found in the models. So there's been this long-standing idea that mid-latitude SSTs don't matter very much for the atmospheric circulation. There's a nice review paper by Joachim Kruschner in 2002, basically is one of the main papers about this. But then there's been some more recent work suggesting that this could be an artifact of not fully resolving the relevant processes. If you go to higher resolution, you might get a larger response of atmospheric circulations to mid-latitude SST anomalies. So then this multidecadal variability of SSTs then gives you more multidecadal variability of the atmosphere. And so just a paper lending some support to this. Here's looking at SST anomalies in the Kuroshio extension region and the response at two different resolutions. Quarter degree, you get this response. In the upper troposphere, at 1 degree, you don't. And then there's been some more regional modeling studies looking at even higher resolution. So here looking at 12 kilometer, or about 1/8 of a degree resolution, showing that you get much stronger ascent if you have a sharp SST gradient, but that you can only get the strong ascent if you have a sufficiently high enough resolution. So if you have 1/8 of a degree, but if you have 40 kilometers, which is closer to 1/4 degree, then you're not fully getting this response to the atmospheric ascent to the SST gradient. So, but then you can't, from these regional model simulations, you can't really think about how this influences a large-scale circulation. On the other hand, most of the existing high-resolution climate modeling efforts, so climate modeling being decade or longer simulations, really tops out at about a 1/4 degree atmospheric resolution. So this includes the high-resolution model intercomparison project, as well as the IHASP effort with CESM. Both of these have only 1/4 degree atmosphere, even though they often go to higher resolution in the ocean. So what we're doing is we're taking advantage of the variable resolution capabilities in CAM-SE and developing a new grid with Adam Harrington doing a lot of the heavy lifting on this effort to design this nice new grid where we have 14 kilometer or about 1/8 of a degree resolution in the North Atlantic, but can still resolve the rest of the globe at the lower 110 kilometer or 1 degree resolution. And so then the simulations I'm going to show are basically a reference simulation with climatological seasonally varying SSTs. And important to note here, I'm still keeping the SSTs at 1 degree resolution. So I'm only changing the resolution of the atmosphere and seeing what influence that has. Then the two experiments I'm running are shown in the bottom here. There's an SST, they're both SST anomalies in the Gulf Stream region. One is an SST gradient anomaly with warm in the south and cold in the north. And one is just a square patch of warm SSTs, raising the temperature by 2 degrees Celsius throughout the whole region. I'm running each of these simulations in this new variable resolution grid, as well as a reference grid at about 1 degree resolution. And just to give an idea of the cost of this, this does take about 35 times the core hours of a 1 degree simulation to run this variable resolution grid, but it's still about 1/10 of the cost of if you were to run this resolution globally. So, and this allows me to run for after some spin up for 15 years for these high resolution simulations. So get some good statistics. And here's the main result. So this is showing the DGF sea level pressure response to these two different SST forcings. In the high resolution, you get these large responses that are significant compared to the internal variations. These are quite large responses of up to or even greater than 4 hectopascals in some regions. This is really big NAO-like anomaly in these simulations. We are extending these out a little bit further to see if this holds up to longer simulations, but all indications so far are that this is a very significant anomaly in the high resolution case. At low resolution, you get a similar response to the warm SST anomaly case, but weaker amplitude, and then you're kind of completely missing the response to the SST gradient case. And in order to get the statistical significance here, I've had to run these simulations out further, which is of course possible because of the lower resolution. Despite these big differences in the large-scale atmospheric circulation response, there's not a very big difference in another quantity that I thought would be relevant, which is the local precipitation over the SST anomalies. If you compare the two different resolutions in these two different experiments, they look pretty similar in the different resolutions. You're not getting some big enhancement of the precipitation in the forcing region. It looks pretty similar between the two different resolutions. Yet somehow you're getting a much deeper temperature response into the free troposphere. So this is showing averaged over the forcing longitudes, the latitude versus height versus pressure cross-section of atmospheric temperature, potential temperature, and then the V and omega winds. So you can see in the high resolution cases, you get this warm anomaly extending up into the free troposphere in both cases. So kind of similar in both of these high resolution cases. You get that similar kind of response, but weaker in magnitude in this 1 degree warm anomaly case, consistent with its similar but weaker large-scale circulation response. And then in the 1 degree gradient anomaly case, you're getting the temperature anomalies instead going more meridionally and not really reaching up as far into the free troposphere. So I think this is, explaining this is key to explaining the differences in large-scale circulation response. How does this temperature anomaly get up there? Kind of hinted at this already with the precipitation anomaly plots, but it's not really a story of differences in diabatic heating. If you look at the diabatic heating, including latent heating and also radiation, it's not hugely different between the different cases in the free troposphere, especially comparing top and bottom. So I don't think that's the difference. But the other thing that's relevant for temperature anomalies in the free troposphere is also what the transient eddies are doing. And so if you look at the energy budget and find the total transient eddy heating as a residual, in the high resolution cases, you're getting that transient eddies are acting to heat the upper troposphere. This is the yellow-orange contours here, versus in the lower resolution cases, and in particular this NE30 gradient anomaly case, you have that transient eddies are acting to cool the free troposphere, so moving heat out of this region. So what I think is going on is basically the transient eddies are moving heat from near the surface up into the free troposphere in the high resolution case, versus you're more energizing the storm track with this forcing and moving heat meridionally in the low resolution cases. And one other interesting quantity I wanted to show that I think is related to this is that you're getting a huge increase in the vertical velocity variance in these high resolution cases. This is kind of an expected result of going to higher resolution, that you get more vertical velocity variance. A lot of this is happening at very small scales where it doesn't necessarily always influence the heat fluxes, but basically you do have a lot more ascent going on within your synoptic storm systems, and some of this is acting to modify the vertical heat fluxes by the synoptic storm systems and latitudes. So this is, I should have said, this is the climatology and contours, and then the response to SST anomalies and shading, and both are increasing by about an order of magnitude as you go from 1 degree to the high resolution. Just checking time, 2 minutes. Okay, so should speed up a little bit. this was all nice and simple so far, but if you add in a quarter degree case, which I wanted to see, do you really need this eighth of a degree to get this response? Things get a little bit messy. You're still not getting the gradient anomaly response, but then in the warm anomaly case, even though you had about the right pattern, just a weaker amplitude in the 1 degree case, now at quarter degree, you're getting something completely opposite. But if you look at the same quantity, what are the transient eddies doing? It's kind of emphasizing the same story. Basically, if transient eddies heat the free troposphere, you get this large atmospheric circulation response. If they're acting to instead move heat poleward, this is then engaging more of a storm track-like response and not getting this big influence on the mean winds. So ultimately, I think it comes down to where in the cyclones the ascent is occurring. In the eighth of degree case, you're getting ascent in the cold front, which can get you anomalies efficiently up into the free troposphere. In the quarter degree case, you're emphasizing more ascent and rainfall anomalies in the warm sector of cyclones, where this can move the heat more poleward and not upwards. And I have full animated versions of these that didn't make it into the presentation computer here today, but if you want to see them, come find me and I can show you the animated versions of these. Oh, never mind, it got switched. It tested before and it didn't work. But basically, the eighth degree is starting to look like more what you're used to seeing from a weather map, and actually resolving all these fronts and the vertical velocities associated with them. And then once you've seen this, the 1 degree simulation really looks quite like a blob in comparison, and it's kind of remarkable that this does do as well as it does, considering we're not resolving all of these frontal features in a 1 degree model. So in conclusion, if you go to 14 kilometer resolution, you get a much larger NAO-like response to warm Gulf Stream SST anomalies that is weaker, absent, or of opposite sign in lower resolution simulations. And this results from a large increase in resolved ascent within mid-latitude cyclones that acts to bring heat up into the free troposphere. And I think the opposite response at the intermediate resolution is coming from preferring warm sector ascent versus cold sector ascent within the cyclones. Kind of out of time here. Just wanted to say that this really has potential big implications for making decadal predictions, because we can predict SST anomalies on multi-year timescales, and if they have a bigger influence on the atmospheric circulation, this is then very important for predicting climate over the surrounding land regions. And this atmospheric response could also influence the further evolution of SST anomalies. I think there's still open questions related to what part of the SST pattern matters. Is this really a realistic response compared to the real world? And can it be reproduced in other models? But I'll end there, and if there's time for a question, I'll take it. Thanks.
Thank you. Do you have any questions for Rob, either online or in the room? Yep, Dylan.
Great talk. I was interested to see that the precipitation changes between the models simulations weren't that different. I'm wondering if you'd get a different result if the ocean were also high resolution. If you were able to resolve mesoscale eddies in the ocean and the sharper frontal zones.
Yeah, I simplified it by ignoring the ocean resolution now, but we're definitely interested in, with ILS simulations, looking into the role of ocean resolution. I wouldn't know how this affects the precipitation response in particular, but we're interested to look into it, and we'll be doing that soon.
There's a question in the chat from Young O. Thank you for the nice talk. Do you see any remote outside of the North Atlantic response differences between the resolutions?
Yes, there are definitely remote influences of this response outside of the North Atlantic, but it's starting to get a little bit harder to get the statistical significance from these 15-year simulations. So I'm hesitant to say anything about those until the simulations are extended a few more years.
Okay, thank you. Our next speaker is Hui Deng from NOAA.
Yeah, good morning, everyone. Yeah, my name is Hui Ding, And my talk is about some relationship between the North Pacific high and upwelling winds along the west coast of North America. And I did this work with Mike Alexander from NOAA and Ming Fan Ting from Columbia University. So here is a schematic for the California current system along the North American west coast. In summer, yeah, on the left, it's North Pacific Ocean, and in summer, the North Pacific is dominated by subtropical high, and we often call this the North Pacific high. And near the coast, equator winds prevail, and these winds move water offshore by Ekman transport and cause coastal upwelling. And coastal upwelling is important because it delivers nutrient-rich water from the deep ocean to maintain a productive marine ecosystem. And yeah, this orange vector is geographic transport. It's also an important component of the coastal upwelling. But in this work, we will focus on the impact of the North Pacific high on upwelling winds only. Actually, several studies already examined the impact of the North Pacific high, especially the surface high pressure cell, on coastal upwelling along the west coast. But results from this paper shows the impact of the high pressure cell has only a small impact on coastal upwelling in summer. The impact mainly occurs in spring and winter. So yeah, so this motivates us to look at the other aspect of the North Pacific high. And yeah, future changes in coastal upwelling has been extensively studied since 1990, and most of these studies were inspired by Buck in 1990, and this paper found coastal winds were getting more and more popular for coastal upwelling in these major upwelling systems. And this study argued this increasing trend will continue in the future. And in this work, we will also look at the future changes in the North Pacific high and upwelling winds a little bit. So we use ERA5 reanalysis monthly data to examine interannual availability and verify against the CESM large ensemble. And then to examine future changes, we use CESM large ensemble, and we use the last 30 years minus the first 30 years to indicate future changes in. So this figure is the summer mean state in the eastern North Pacific, and the shading in each panel is 500 hectopascal pressure. Vertical velocity we are currently sharing. Okay. Where is the mouth? Oh. Okay. Disappears again. Thank you. Yeah, sorry.
Yeah, you're right. Bias is impossible to find.
Yeah, wow.
Oh, okay.
Oh, thank you. Okay, I cannot go back. Please go back one.
You can go back.
Okay. So where am I? Okay. Yeah, shading in these two panels is 500 hectopascal pressure vertical velocity, and the vectors are surface winds at 1,000 hectopascal, near surface winds. The left panel is ERA5, and the right panel is the large ensemble. And we can see near surface equatorward winds near the west coast near California. And yeah, these winds are upwinding favorable since they point to the equator in the northern hemisphere. And we also notice these equator-ward winds occur in regions only with a strong subsidence above. Actually, this is consistent with the vorticity balance in the atmosphere, according to previous studies. And we can see this relationship also along the west coast of North America. So this figure shows a cross-section along the west coast of North America, and the x-axis in both panels shows latitude of coasting grid cells, and the y-axis shows the height. And shading in both panels shows meridional wind from each level only. And we can see near the surface, equator-ward winds occur only in the southern part of the coast, with a strong subsidence above, and this relationship is also noted in the large ensemble. So this motivates us to define omega 500 index to measure the strength of the subsidence in this black box on the right. And for a comparison, following previous studies, we also define a sea level pressure index to measure the surface high pressure seal shown on the right. So since we have these two indices, we correlate them with surface meridional wind in the eastern North Pacific. In this panel, it's the correlation between the sea level pressure index with meridional wind. And we can see the surface high pressure seal is only weakly correlated with wind in the coastal areas. But on the right, the middle panel shows the subsidence has a strong impact on meridional wind, surface meridional wind along the coast, and the correlation is about -0.6 and -0.7. So this is meridional wind only, and we can also consider both tau x and tau y, and then we can calculate upwinding favorable alongshore wind stress for each grid cell, which is this right panel. So y-axis shows the latitudes of each coasting grid cell. We then correlate the upwinding favorable alongshore wind stress with the two indices. And again, we can see the x-axis shows the correlation values. Again, we can see the surface high pressure cell is only weakly correlated with the upwinding favorable alongshore wind stress, which is blue line, and the correlation is about 0.3 or need above. But on the other hand, the subsidence has a strong control and account for about 50% of the interannual availability in this latitude between 33, some grid cells near California coast. The correlation is more than 0.7. So this is interannual availability. And in the following slides, we show some work for future change in the North Pacific high and upwinding winds. So this is done by the ensemble mean epoch difference. And so the last 30 years minus 30 years at the beginning. So this figure shows the epoch difference in sea level pressure on the left and surface pressure on the right. On the left, the dashed and solid contours show the surface high pressure cell. And we can see sea level pressure increases only in the northern and southern part of the high pressure cell, but not much in the middle of the cell. So in the end, the future change in sea level pressure index on the bottom right it's pretty small and it's not significant. And yeah, interesting. We can see, we see a lot of increased sea level pressure in continent, and this is also confirmed by surface pressure. So on the other hand, we do see significant future change in 500 hectopascal vertical velocity and surface wind stress in the bottom two panels. And in the upper two panels, it's summer mean state from the two different, from the earlier and the late future epochs. And the right panel minus the left panel gives the epoch difference in 500 hectopascal vertical pressure, vertical velocity, and the surface wind stress. And we can see the subsidence in this area decreases. But we see, on the other hand, we see anomalous subsidence in the north. And accordingly, on the right, we see polarward wind stress, surface wind stress, and the equatorward wind stress in the north. And we can see this maybe better along the west coast of the North America. So this is the upper panel is the cross section along the west coast. It's epoch change, it's epoch difference, and the bottom panel is epoch difference in upwelling favorable longshore wind stress. Hatching and dots indicate 95% significance. Now we can see this blue dot. This blue dots. This means upwelling favorable longshore wind stress decrease significant near I believe it's California coast, but in the north the upwelling wind stress increase significantly, and and above we can see anomalous ascending motion near California coast and descending motion in the north. Okay, this one is the last one. So this one is the intermember scatter plots between 500 hectopascal pressure, vertical velocity, and so it's x-axis, and upwelling favorable longshore wind stress for y-axis in the south and north. And we can see, in the south the correlation is very high. So this suggests future change in the subsidence modulate about 50% of future change in upwelling favorable longshore wind stress in the south, actually it's California coast. And this relationship also exists in the north, and the correlation is even higher. So okay, I'll be short here. The message is the subsidence has a strong or account for a large fraction of interannual variability, and modulate future change in upwelling favorable longshore wind stress along the west coast of North America. Thank you very much.
Thanks. Any questions for Hui? And I guess I'm wondering, can you then look at, the large-scale metrics that you've looked at? Is there consistency across models? And
yeah, I agree. Yeah. Thank you. Yeah. I think we will do that later.
Okay.
I think it's pretty robust in CMIP 5, but it's not clear yet about CMIP 6.
Okay. Yeah. Thanks. Okay. Thanks a lot.
Thank you.
So our next speaker is remote. Fabrizio Falasca, are you there?
Yeah.
Okay, let's, just leave it there. So I guess, do we have to stop sharing, or should I be doing that here?
I'll try to share here.
Yeah, we need to stop sharing our one,
Okay,
but
okay.
just a second.
No problem. Should I share or?
I think we're still waiting on. Okay, now
Okay.
it looks like you can share now.
Okay, let me try.
Yeah, I'll jump in at 12 minutes to give you a warning. So yeah, feel free. Oh no, I guess you can't share yet because I can. Yeah, in the meeting we're still sharing our
cannot
screen.
yet. Okay. 5:15.
Okay, are you able to share now?
Sorry. Can share the screen.
No, yeah.
System preferences.
Okay, maybe now. No.
No, it tells me that I have to close Firefox and then open it again.
Okay, hold on a second. Let me just check. Is this his problem or our problem?
Let me try.
If you could please close Firefox and reopen it like it's asking.
Okay, you might have to log off and log back in. Oh.
Okay.
Oh no.
Oh, what a mess. Sorry.
I think Chrome normally works a bit better. But if
Okay, yeah, it's not clear to me how to do it.
do you have Chrome? Can you log off and log back in on Chrome? Oh, or we have your slides here.
I can try to quit Firefox 1 second and then jump back.
Or do you feel like, could you just tell
it
me to
okay?
advance the slides and we could look at them here? Does that work for you?
Hello?
Hi, can you hear me? Hi, can you hear me? We can advance
for some reason I cannot hear anymore anyone.
Oh.
Yeah, I cannot hear anything. I'm
Can
sorry.
other people online hear us?
I don't know if anybody's talking.
Yes, I can hear. Yeah.
Okay. Let me send a chat then. Okay, so we can we share these slides to the Google Meet?
Okay, I cannot hear anyone in the audience, so it's like everything is silent here. Go on the first slide. This would be the, okay, good. If you have to ask questions, just write it because I cannot hear anything. So hello everyone, sorry for these little issues. I will present today a new methodology to quantify probability changes in probability distributions directly from time series data. And I will do so by focusing on an application and sea level rise as an application. Next slide. Next, okay. I will start from introduction and motivation, focusing first of all on global regional sea level rise, and then I will make the case that is useful when trying to understand climate variability and change to actually quantify changes in the full probability distributions. I will then propose a methodology to quantify sources of changes in probability distribution directly from time series. And I will show some results focusing on sea level rise or an application across observation, in my case, tide gauges data and GFDL model. And then I will go through conclusion if there is time. Next. It is well known nowadays the global mean sea level has been rising. On the left panel, you see a figure from the paper of Frederick et al. In 2020, where we see an increasing global mean sea level from 1900 to 2020. And I would like you to focus on the blue curve showing changes in the observed reconstructed sea level. And it's clearly going up, and there is in the last decades an acceleration. And it's going up with an average rate of this slope of 1.35 millimeter per year. On the other hand, if we look at regional sea level, here from altimetry from 1993 to 2014, we see that there is a lot of heterogeneity in these trends. And this heterogeneity come mainly from local variability, local climate variability. So from changes, local changes in winds, ocean patterns, ocean warming patterns, and modes of variability. Next. And when we usually quantify trends or changing from sea level time series, in general from time series, the first thing we do is to quantify linear regression, so trends of the time series. This allows us to quantify changes in the conditional mean of the distribution. In the case of sea level, conditional mean of sea level in condition to time. We do so, therefore, by ignoring higher order changes in the distributions. However, next, to better understand climate change and climate variability, it is useful to actually understand the full probability distribution, as climate change may impact variance, asymmetries, and tails of the distribution too. Next. So what I'm going to show you in this talk very briefly is a way to actually do so and to decompose changes in the distributions in an interpretable way. And I will do this in a pedagogic way, next slide, by focusing first of all on some synthetic time series, and then going through sea level rise and tide gauges and models. So consider a time series of this kind. You have time on the x-axis and a variable s, and we generated this time series ourselves. Next slide. If you compute a linear regression, you would find that there is a trend in this time series and there is a positive slope. So this trend is going up. This means that the conditional mean of the distribution, so conditional mean of the variable s conditioned to time, is going up. However, as you focus on the conditional mean, we can nowadays also compute conditional quantiles. So conditional median or conditional quantile 0.05, 0.95. Next slide. And we can do this using methodology called quantile regression. More than that, we can actually focus on a lot of different quantiles, not just these three. Next slide. And here, click next 3 times. And here, what you have are changes in the that's it. You can see changes in all the quantiles of the distribution from 0.05 quantile to 0.95 quantile. On the x-axis, you see the probability level of each quantile, and on the y-axis, there's slope. Next slide. what you see here is that this picture gives you a lot of information on how the probability distribution is changing. First of all quantile slopes are actually greater than 0. This tells you that the mean of the distribution is increasing. Next slide. On top of this, the variance seems to be changing too. And you can see this because the changes are symmetric over the median. So P equals 0.5. And larger quantiles are changing faster, and smaller quantiles are changing slower in respect to the median. So here we know that in this time series, probably both the mean and the variance may change. Next slide. But what about other higher order moments? If you want to think about skewness, kurtosis, or fifth moment, and so on, it starts becoming more and more difficult to interpret with this plot. Also, how to deal with n time series where n may be 10,000 time series. We cannot anymore look at this plot. And how to deal with statistical significance, where it may involve some bootstrapping or reshuffling and so on. Next slide. And a strategy that was first proposed, as far as I know, by Karen McKinnon in a JGR paper in 2016, is actually to reduce the dimensionality of all these quantiles and focus on how changes in moments of a distribution can explain these changes in quantiles, and specifically independent changes in moments of a distribution. Next slide. So here we show, inspired by the methodology proposed by Karen McKinnon, we actually tried to look at this framework in an analytical kind of way. Here you have quantiles that I call them QP, quantiles Q and probability level P. So if quantile QP equals 0.5, it means that you're looking at quantile 0.5 or the median. We're looking at non-stationary distributions, so these quantiles depend on time, and depend on time through all the moments, and here we do a truncation, and we just look at the first 4 moments. Next slide. And we focus on linear changes, and you can write it down simply as derivative of the quantile over time, and what you will see is that changes in quantiles depend on change in quantile over each one of the moments, and then changing on the moments over time by simple application of chain rule. Next slide. And by assuming a relatively small deviation from Gaussianity, I'm not going to give a lot of details. You can find this, but I have it later in backup slides. But you can find a relationship between, next slide, the slopes computed in the quantile regression step and the moments, dmi, dt, through some polynomials. And these polynomials are Hermite polynomial of the quantile function of a standard normal. But what it means is these polynomials are actually orthogonal in the probability space. From 0 to 1, these polynomials are all orthogonal to each other. So next slide. So quite beautifully, what they quantify these polynomials is how quantiles of a distribution change when you shift its moments one at a time. So if I change the mean of the distribution without changing any one of the other moments, the quantile will change as a constant, and this constant is B1P, so the blue curve. If you change just the variance, but not the mean and not the other moments, then the changes will be shown by the orange curve, B2P. Next slide. And so on for skewness and kurtosis. So we obtain a simple formula where we have on the left side the computed quantile regressions. So these are the slopes and quantiles I showed you before. And on the right side, you have these polynomials that we also have. And the only unknown is these changes in moments. So you can fit these changes in moments by a simple linear regression using this basis, this polynomial basis. Next slide. And so what you see here is that this is an example, and we have many of these, but if you focus on the top panel, so panel A and B, you see a time series that is generated by a drifting Gaussian distribution. You see that in this time series, both the mean and the variance is changing. And on the right side, you have the changes in quantiles, so the slopes in quantiles from 0.05 to 0.95. And what you would see is that, in blue, you have the changes in quantiles, and in black, the projection over these polynomials. Next slide. And if you do some statistical significant tests that we have no time to go over right now, you will see that the only two polynomials that you actually need to explain these changes come from the mean and the variance, as we know. And for the next time series that you see on panel C and D, this is a time series that is generated by a beta distribution. And here we know that changes come only from variance, skewness, and kurtosis, and the method is actually able to find these changes. Next slide. So we're trying to apply this methodology, also next slide, to sea level rise as a first application. Here we focus on daily sea level, and we focus on the period 1970 to 2017. These are tide gauges data downloaded from Sea Level Center in University of Hawaii. Whenever you see a dot, it means significant, and when you see an X, it means not significant. So what this tells you is that changes in coastal sea level, at least for the tide gauges that we have available, come especially from changes in the mean. So in the mean, basically all changes in the mean are significant, while changes in higher order moments appear not significant under our statistical significant test. So this means that you can explain these changes in sea level distributions in the observed world as a simple shift of the probability distribution towards, in general, higher values. So one obvious critic here is that maybe we're using just 50 years of data, and it may not be enough to actually capture changes in higher order moments such as skewness and kurtosis. We know that this may not be the case by synthetic dataset, but anyhow, next slide. We look at changes in sea level for time series that have at least more than 80 years of data, focusing on daily sea level. And what you see here is that still the conclusion still stands. The main changes come from the mean and not from variance, skewness, and kurtosis. Okay, so this motivated us to try to understand how changes in probability distribution may happen because of in model outputs or with CO2 experiment. I have 1 minute more. Next slide. And the good thing about using a model is that even if it's biased, we can understand, we can decompose sea level in different ways. And here, next slide, we rewrite sea level as a summation of dynamic sea level, which is a summation of changes in water column mass and local steric effects. And this you can just think of it in a very simple way as local changes in sea level that comes about just because the ocean is moving. So there are currents, and so sea level is changing locally. And then, next slide, another term that is the inverse barometer, which shows us how changes in sea level can be driven by local changes in sea level pressure. An example is strong convective processes would give a strong change in sea level that is just local because of convection. So next slide. We first focus on GFDL CM4 data. Here is 0.25 degrees remapped to 0.5 degrees. We focus just on from the -60 to 60, so 60 south to 60 north latitude. And we look at daily sea level, and what we found is that if you focus on the historical run, we have the same information that we have obtained in the observations. In this sea level decomposition, we do not look also the global mean sea level. So you would have to add a positive term to all these trends. But it doesn't matter because we look at higher order moments, and this is not affected by global mean. So variance, skewness, and kurtosis are not changing. Next level. Next slide, sorry. And what we have is that, however, even if in the historical run we see no higher order moment changes, we start seeing emergence of higher order changes in runs such as, in this case, 1% CO2 a year from pre-industrial. And on the left side, you have dynamic sea level. On the right side, dynamic sea level plus inverse barometer. And you start seeing the changes in variance and skewness are already present in dynamic sea level, and changes in higher order moments are always amplified when looking at the inverse barometer. Next slide. And I have 2 more slides and I'm done. Can you go on next slide? And also next slide. This is a simple example of changes in the Mediterranean Sea in this simulation without looking at the global mean changes. So you will have to take that time series and put it up of a trend, but it would not change the probability distribution. So we'll just shift it. And what we see is that the methodology would tell you, okay, the changes come from mean, skewness, and kurtosis. And in fact, if you look at the simulation histogram in the first 40 years and last 40 years, you see that these are the changes that actually happen in this sea level time series. Okay, next slide. As conclusions, I will not go over it because I'm already over time, and I'm sorry about the technical difficulties. The main point is now with this methodology, we would like to apply this methodology to sea level distributions or other variables too, like temperature in our case, in open ocean, across different models and scenarios, and trying to understand what is the relationship of these changes coming from model error or just from internal variability of the system. Next slide. And also understand something about the dynamics. And this is a preprint that we have out, and luckily just received some minor revision that you can read. And I will, for question and so on, I really cannot hear anything. And so I will put my email. I will try to answer message, in the chat, but maybe the smartest way is if I put the email and people that are interested can write me on the email. Anyhow, thank you very much.
Okay, thank you. So since Fabrizio can't hear us anyway, we won't take questions in the room, but if any of you online have questions, you can go ahead and put them in the chat and maybe have a discussion in there. So here we'll move on to the next talk, which I believe is also a virtual talk. But Aurora, are you able to, can we stop sharing our screen so that they can try?
That sounds good.
Okay, does it, it looks like we're still sharing our screen.
Yeah.
Should I be doing something down here? Our screen is still sharing on the Google Meet, so can we stop that or?
So we're going to present from here.
No, we want to have her try sharing online.
We can see her slides.
Well, we're sharing the slides here in the room. I just wanted to
I
give
see.
a chance to do it online. If it doesn't. Oh, okay, I can do it here, I guess. Sorry, I was waiting for you. I thought that, right, okay, try now.
Sorry, 1 second. I just have to give it permissions to do so.
Yeah, so we've just stopped sharing in the room and hopefully you can do it there.
Okay, it says I have to restart Google Chrome.
Okay, would it be straightforward for you to just tell me to advance the slides and we can share them here?
Sure, yeah, I can do that.
Okay.
Sounds good.
Oops. Okay, take it away.
Great, thanks. Yeah, so today I'm going to talk about estimating trends in freshwater fluxes using linear response theory. And this is work that's been done with my PhD advisor, Lorzana. Next slide. Great, so to start off with some background, estimating the hydrological cycle over the historical record is often approached using salinity changes because it's hard to directly measure surface freshwater fluxes. So the idea is that the amplification of the evaporation minus precipitation pattern imprints on ocean salinity, and then you can use ocean salinity to try to infer what those freshwater flux changes were. So to look at the salinity changes over the historical record, we can look at the plots on the right. So the top plot is the mean surface salinity over the period 1975 to 2019, and then the bottom plot is the change over that same period. So it's the mean of the last 5 years minus the mean of the first 5 years. And so broadly speaking, what we can see is that regions that are salty are getting saltier and regions that are fresh are getting fresher if we compare those two plots. And this to some extent is an imprint of that kind of amplification of the freshwater flux pattern. But the complication, or like an additional wrinkle in this, is that the change in local surface salinity isn't just affected by surface fluxes. So if we were to look at the tracer equation and think of the tracer here as salinity, it's affected by the sources minus sinks term that's shown at the end, but it's also affected by the other terms, which here would be ocean transport. Next slide, please. Great. So quite a few studies over the past decade have worked on this problem of trying to estimate hydrological cycle amplification from salinity. So here the y-axis is amplification per degree Celsius, and then the x-axis is various studies. So they've used quite a few different methodologies, so I won't go into all of it. But for example, Dirac et al. 2012 and Sika et al. Both use surface salinity, and then the other ones that are shown there primarily used interior salinity. Next slide. Great. So the goal with this work was to add a complementary estimate onto the previous work that we're showing on the right. And we aimed to do a couple of things with this new estimate. So the first thing is we want to focus specifically on surface salinity because observations at the surface are a little bit more certain than in the interior. And then the other thing that we want to capture is that the impact of ocean circulation change is primarily regional or local. So when people talk about salinity pattern change, often what they talk about is an amplification. So the entire global pattern like amplifying in its existing form. But if we look at the map that's shown on the slide there, which is from an ocean-only model that's forced with just heat fluxes. And so we're seeing the impact of salinity basically being moved around by heat flux-induced ocean transport change. And so what we can see is that here there are regions where the signal is very strong. So for example, in the Atlantic, there's quite a large salinity change just from that ocean transport change, but it doesn't look like the existing pattern. So it doesn't look like a scale up or down. Next slide, please. So to give away the answer from the very beginning, the orange dot that's been added to the plot on the right is the estimate that I'm going to talk about for the rest of this presentation. So we ended up with a value of about 4.5% plus or minus error, which is within range of some of the previous studies, but is definitely below the Clausius-Clapeyron rate of 7% and adds some confidence that the amplification is below Clausius-Clapeyron. Next slide. So the first step that we took in this methodology was trying to characterize the salinity pattern into distinct regions. So the idea was that if we broke up the salinity pattern, then we can talk about how the salinity pattern is changing in terms of trends in time in a couple of regions. So on the left in light gray is the surface salinity distribution. And then on top of it, we fit a Gaussian mixture model with 6 mixtures. So going from less salty up to the saltiest, which would be number 6. And then on the right is how a map of the ocean surface would then be clustered based on this mixture model. So the idea is for each point, we categorize it into one of the 6 depending on the salinity at that point in the climatological mean. So here the bluer colors are fresher areas and the yellower colors are saltier areas. Next slide, please. So the next ingredient that we need for this method is linear response theory, which broadly speaking finds the change in statistical properties of a dynamical system because of a forcing. So here we're considering the dynamical system to be the climate system, and we're going to apply linear response theory so that we can talk about the change in salinity and temperature in each of those Gaussian mixture model regions. So in each of the 6 regions that's shown in the plot on the bottom right there. So basically, linear response theory allows you to write the change in these time series as equal to the convolution between the response of a step function and the strength of a forcing time series. Next. So yeah, underneath there is showing that in equation form. So here delta y is the change in salinity in temperature regionally, and then the r function there is the response to a step function, and then the f is the strength of the forcing over time. Next, please. So I won't talk about this too much, but basically to be able to apply this linear response theory expression, of course, we need those responses to step functions. And we're going to take those from the ocean-only FAFMIT project, which is basically an intercomparison project where ocean models are forced separately with 3 different flux perturbations, freshwater fluxes, heat fluxes, and wind stress change. And these are all associated with a doubling of CO2, and they're applied separately to those ocean-only models. Next. Okay, so the final setup of the problem is basically to assume that these regional time series of salinity and temperature are linear combinations of the response to heat flux perturbations, freshwater flux perturbations, and wind stress change. So that's shown in the boxes on the slide there. On the left, again, we have the time series of salinity and temperature change, and then we're saying that can be broken up into those 3 components. Next. So to each of the individual components, we apply the linear response theory expression that I talked about on the last slide. So we're expressing these changes in salinity and temperature in terms of those step functions and the magnitude of the forcing for each of those 3. And so what we're going to focus on here is that, like, using this expression, we can solve for the strength of the forcings that are attributed to the time series. And so we're going to focus on the freshwater flux forcing strength, but as we solve for that freshwater flux forcing strength, we're kind of inherently taking into account the salinity and temperature change that's happened because of the other 2 components as well. Next slide. Okay, so eventually we're going to talk about applying this to observations, but before we applied it to observations, we tested the method on the CESM large ensemble data over the period 1975 to 2019. So first I'm going to talk about applying it to the CESM ensemble mean. So in the bottom right, for example, is the change in salinity in the ensemble mean. And there would be kind of a similar plot for the change in temperature. So this is in each of the regions, and we're showing the trend in time. So the method that we just talked about makes an inference from like these time series and gives us a amplification as a proportion of the step forcing pattern. So the kind of output of the method is as a proportion of the map that's shown in the lower left here, which is the freshwater flux step forcing. And then what we're looking at in the top right is comparing 2 things. So the first is just applying the method to salinity and temperature, and then we can compare that directly against model fluxes. So the kind of top row there is from the linear response method, and we get a value just over 0.35 times that step forcing map. And then the bottom is from model fluxes, and we can see that the value that we got from linear response theory is well within the kind of error range of the true value from model fluxes. So for the ensemble mean, we find that we can recover the true fluxes is the takeaway here. Next. And then the next thing we wanted to test on is individual ensemble members. So the idea here is that observations are to some extent kind of equivalent to an individual ensemble member. We can't take a true ensemble mean. And so what I'm showing on the bottom right is kind of in the thick lines is again the ensemble mean trends in salinity. But around region 6 in the lighter yellow that's hopefully visible, I'm showing the different members that are making up that ensemble mean. And of course, each of those trend lines has individual members making it up, but I'm just showing for region 6 for clarity of the plot here. So the idea is that when we apply the method to each of these individual members, we are not able to recover the true response for each of the members. And the reason for that is because some members are much more dominated by internal variability than other members. So if we look at the spread of those yellow lines, we see that there's both a spread of forced responses and there's a spread of the amount of internal variability. And so for members that have a significantly, or like a large enough signal to noise ratio, we are able to recover the true response. And for members that are dominated by internal variability, we can't see the forced response, and so we can't recover it. So what we find is that we are able to recover the true response for a subsection or a subset of ensemble members, provided some significance criteria on salinity trends. Next slide. Okay, so now that we've tested on CESM model data, we're going to turn to observations. So here we're looking at salinity and temperature data from Cheng et al. 2020. And the first thing to note here is that this data kind of easily meets and beats the significance criteria that we talked about on the previous slide. So the forced response is clearly visible beyond the internal variability. And so we proceed with applying the method as we did before. So we find an amplification in terms of the FAFMIT perturbation of about 0.3, which is kind of similar to the CESM ensemble mean. And we convert this to a percentage amplification per degree Celsius and end up with around 4.58 plus or minus some error. Next slide. Great. Yeah, so that 4.58 number is the orange dot on the plot on the right that I also showed at the beginning. And yeah, so I'm just going to conclude here. So ocean transport change is primarily affecting surface salinity regionally. We came up with a method that takes this effect into account, and we tested it on CESM model data, and we found that we were able to find the true amplification in this model data. And then we applied it to observations, and we found that it agrees with many of the previous estimates of hydrological cycle amplification. The caveat here is that error bars are probably a lower bound because we're not capturing all sources of uncertainty. But nonetheless, I think the takeaway is that this adds some confidence that the rate of amplification has been less than Clausius-Clapeyron, and it's an additional data point to compare models against. Cool, thanks.
Great, thank you. Are there any questions in the room or in the chat? Yep, Gemma. Yeah, I think they can hear you now.
Cool. Just to clarify, you said that you weren't getting a significant change with single ensemble members, but you were from observations. Is that a correct understanding? And if so, why is there a difference between the individual ensemble members and the observational time series?
Yeah, so it wasn't that I found it. So basically a subset of the individual ensemble members had significant trends. So of the whole set, about 7 of them met certain significance criteria that meant that we could recover the true response. And then in observations, we also easily met the significance criteria. So I think the takeaway is that they're closer to a subset of the CESM ensemble members in terms of their signal to noise ratio.
Thank you.
Thanks.
Okay, thanks a lot. Yeah, feel free to carry on with any questions in the chat. I guess we'll move on now to the last speaker of this session, I believe, which is Gemma.
No one told me.
Oh, sorry, I forgot. My bad. Okay, I think it's good now.
Cool. So there's a lot of things in the Earth that we don't understand that are highly variable that we'd like to understand, starting from a very broad outline. And the one that I've been looking at for the last year is Antarctic bottom water and the variability of the transport of this water mass. And I've been using a slightly unintuitive way of measuring it from satellite gravity observations. And because it's a bit of an unintuitive way of measuring, I've been using an ocean model to develop a method to use it and to work out how useful this data might be as a proxy for Antarctic bottom water. And then I'll show you a few results. So setting the scene here, Antarctica is quite cold, and the ocean around Antarctica is slightly less cold. This means that when we have winds blowing down off Antarctica, they cool the surface of the water and form sea ice, and that rejects salt, and we end up with...
There's no other microphone here, is there?
I don't know.
Interfering with it.
I can try and speak more quietly.
No, I think it should be fine. Where's the other roving mic? Oh,
If you could speak louder, actually, that would be fantastic.
Okay, I can speak louder. So just pretend I haven't got a mic on. Cool. So we end up with a mass of cold, salty water at the continental shelf, and that's denser than the surrounding water, so it flows down over the continental shelf into the bottom of the ocean. And it mixes with other waters along the way, and what we end up with is Antarctic bottom water flowing into the bottom of the ocean and drawing in other waters to replace it. And that's forming the lower cell of global meridional overturning circulation. Zooming out, here is global meridional overturning circulation. We have Antarctica in the centre, and branching out from that, the three main ocean basins. And Antarctic bottom water fills the bottom of all three of those ocean basins. So anything moving heat or carbon dioxide around in the bottom of the ocean basin is coming from Antarctic bottom water transports. So it can impact the climate, and it could be responding to climate change, but we don't actually have many measurements of the variability in Antarctic bottom water transport. So we're not sure what's going on or how it might be responding to climate change. What we do know is that it seems that volume has decreased from temperature and salinity observations, but the way that the volume is defined using temperature and salinity observations means that this could just be an artifact of changing water mass properties rather than changing currents. And I wanted to measure the change in currents using a completely different tactic. The GRACE mission is a pair of satellites that orbit the Earth, and they've got a really accurate distance measurement between them. So if the lectern is a large mass and the satellites move towards that large mass, the one in front is going to speed up first as it gets closer, and the distance between the satellites will increase. And then as it flies over the mass, the one behind will speed up a bit, and then it gets to the other side. And the first satellite will slow down, and the distance between them will decrease, and then they get both past the mass, and the distance changes again. So by doing lots of complicated maths, you can turn this distance metric between the two satellites into an estimate of mass over the Earth and gravity over the Earth. Now, the Earth is a very large, heavy chunk of rock. So the dominant gravity signal of the Earth is the big bit of rock. But the rock doesn't change much over time. So if you subtract the time mean gravity signal, then what you're left with is changes in water mass over the Earth. That's a really simple ocean, and if you put some extra mass on the top of the ocean, that directly corresponds to a higher pressure at the bottom. So these GRACE gravity measurements are measuring ocean bottom pressure. If we move to a slightly more realistic ocean, where I've got some sort of surface waters and then an Antarctic bottom water layer at the bottom, the GRACE satellites are measuring pressure at the bottom of the ocean down both sides and across the bottom. And specifically, they're measuring the pressure at the bottom on both sides of the layer, or just on the sides of the layer. And geostrophic balance tells us that if you have some zonal pressure gradient, because you know pressures on both sides of a layer, then you can use that to infer the geostrophic velocities of that layer. So in the southern hemisphere, if you have a positive pressure on the western boundary and a negative pressure on the eastern boundary, then that corresponds to a velocity into the screen. So, very simple conceptual model. Theoretically, the GRACE satellites should be able to measure Antarctic bottom water velocities. But the accuracy of the GRACE satellites is about that much water height, which is about the same as the uncertainty, or size of the signals that we're looking for in the Antarctic bottom water signal. And the GRACE satellites also have a spatial resolution of about 300 kilometres, which is quite large and might not necessarily capture the exact pressure location that we're after. So I'm testing it with an ocean model. This is the Australian ocean model, Access OM2, and I'm using it at 0.1 degree resolution because at that finer resolution, it does a good job of capturing Antarctic bottom water dynamics and flows. And I'm estimating Antarctic bottom water across a transect. So one example here is in the Pacific Ocean, and then I'm looking at meridional velocities in different density classes. At the bottom, we have 2 density classes going northwards, and so I'm calling that my Antarctic bottom water that I would like to be able to measure. I'm emulating GRACE just by taking the ocean bottom pressure anomaly, which is what it should be measuring, and then averaging it to the really coarse spatial resolution of the GRACE satellites. And that's my emulated GRACE product. And then I'm linking the two of them just using a linear sum. So I'm assuming that you can find Antarctic bottom water as some weight multiplied by one particular pressure or GRACE grid point plus another weight times another grid point, another weight times another grid point, and so on and so forth. And then I find those coefficients or weights using a simple linear regression. And that's what I get. So before I was showing pressure anomalies on this grid, and I'm now just showing the coefficients that I would multiply those GRACE grid points by in order to reconstruct Antarctic bottom water. And I'll flag that we have a patch of largely positive weights on the western boundary and a patch of largely negative weights on the eastern boundary, which corresponds back to that theoretical geostrophic balance link that we have positive pressures and negative pressures on different sides of the basin corresponding to northward transport of Antarctic bottom water. Theoretically, it checks out. And it also lines up pretty well if I test it with data from a separate model run. So same model, different set of forcings so that it's not just learning or overlearning to the data set. So we've got fairly high skill, fairly low root mean square error. That suggests that the reconstruction, so the red dashed line is given just the emulated GRACE data, what do I think Antarctic bottom water would be? And the black is the measured Antarctic bottom water in the model. And they line up pretty well. And then we add that 3 centimetres water height equivalent of uncertainty, and we get slightly lower skill, but still fairly decent. And that lines up surprisingly well, and that's because I spent several months trying to optimize it. So there's so many different meta constraints going into exactly how the method works. And if you don't include the noise, it doesn't matter. And then as soon as you include the noise, individual metrics make a lot of difference. That's one example, just looking at, do I use a little tiny bit of GRACE data or GRACE data for a larger width of the entire ocean basin? And if you don't include the noise, it looks like you max out at around 8 to 10 degrees of latitude, and it's not worth including any extra data. But as soon as you start considering the uncertainty in the GRACE satellite observations, then it starts to matter that you're including more data to average out that noise. And I guess the moral here is, if you're trying to mimic observations, then you can't just mimic them in a perfect world in the model because you might miss some opportunities to improve your reconstruction. You need to include things like resolution also makes a massive difference, and the noise, the uncertainty in the data. Anyway, I verified that reconstruction method with 2 other models. So the top is the same ocean model, access again at 1/4 degree resolution. It lines up fairly well. The bottom is GFDL OM4, which is using MOM6 instead of MOM5, a different ocean model configuration. It has a slightly larger root mean square error. The skill, like signal and noise, is awful because the bottom one was run with a repeat year atmosphere. I didn't have access to any data with an annually varying atmosphere. So the signal in this run is unrealistic, and I'll be fixing that later. But I can take, I can take the estimate of error, like the root mean square error from that, as a measure of the uncertainty. Okay, I can't change slides.
Yeah, click on it.
I am.
And drag a couple of times. Okay.
There we go. So we get a reconstruction of Antarctic bottom water in the West Pacific. You can do the same thing for the whole Pacific Ocean. And so that is the first estimate of Antarctic bottom water interannual variability in the Pacific Ocean. And you can see that there is variability beyond the magnitude of the uncertainty. The error bars are a little larger than I'd like, so if we could have better GRACE data, then that would make things a lot easier. That's where most of the error is coming from. There's a little bit from the model differences. And there isn't any significant trend. So you can look at it and say, oh, it might be decreasing with time, but it's absolutely not significant. It doesn't really answer the question of whether declines in transport are leading to this decline in volume, or if it's just changes in different water mass properties. Same thing applies to the rest of the ocean, the other ocean basins, that you have variability, sort of changing from year to year, but no significant trends. And summing up, we got the first estimate of Antarctic bottom water transport variability and how it might be changing in response to climate change, but we don't actually get any answer for what it is doing in response to climate change. And if you're trying to emulate any observations, it's important to include the uncertainty, the coarse resolution, and the actual characteristics of those observations rather than being as close as possible in perfect model world. And you can use models to work out how those observations might be used. And I'm happy to take questions now or by email.
Great, thank you. Is there one quick question for Gemma? Yeah, Aisha.
So when you calculate the Pacific transport, you tend to the East Pacific to New Zealand. Why not go to Australia?
Because there's not much going through there, and because the theory says you want to have a basin with walls on both sides. So I tried splitting basically every time the topography came up above the Antarctic bottom water layer and then back down again. And so I get the West Pacific and the East Pacific, and then I also tried in the gap between Australia and New Zealand, but the GRACE resolution is like 300 kilometres and you get 2 or 3 tiles in the gap, and you actually don't get any useful data out of it. And then if you look at the model, no Antarctic bottom water actually gets out through that gap into the rest of the ocean. A bit comes up and then just stalls.
Okay, thanks a lot. So we were supposed to have a break now, but we're precisely at the end of the break in terms of time. I guess I'll take a survey, and I feel like there's 2 things we could do. Either we could have a very quick 5-minute break. We have 3 talks after the break, and then we'll have a 10-minute break before the seminar, assuming there's no technical issues. Or we could just power on through and then have a 15-minute break before the seminar. Who wants option 1, having a 5-minute break now? Who wants 2? Who wants option 2? Okay. Majority's option 2, but if you need a break, feel free to, go and have one. And so I think we'll carry on then. Let's make sure people are, so Danielle, let's see if you can share your screen. I stop sharing.
Hi. Can you hear me, first of all?
Yep, we can hear you.
Perfect. Let me share my screen. 1 second. Let's see if this works. Do you see the screen?
Yep, it's not in full screen mode yet, but we see the slides.
And now is it in presenter mode?
No.
You don't see it?
Yep, now it's good.
Is it in the full screen mode? Okay,
yep,
great.
It's full screen.
Cool. Yeah, thanks for having me. I'm sorry I can't be there in person. So I am Danielle. I'm a postdoc at NCAR and CSU. And I'll be presenting some really preliminary work. It's kind of experimental, and I've been working on this on and off with Clara Desser, Dave Lawrence, and Jackie Schumann at NCAR. So my focus is extreme fire weather, and the motivation is pretty simple. We have been seeing observed increases in fires and burn area in the Western US for the past 3 decades or so. This figure is from Apazaglu from last year or 2 years ago, and you can see that there's been a steady increase in the area burned over time.
A second, Danielle. I think we have a couple of problems. So in the room, your slides are not advancing, and other people online, can you see the slides?
Oh, sorry. Let me try something else.
Okay. Okay.
Sorry about that. Let me try one more thing, and then I'll have you share them if not. Screen 2. Sure. 1 second. Do you see anything right now?
See it in your presenter mode. I guess if you do the swap displays, it might be fine.
Is that good? Is it advancing?
Yes. That looks good.
Okay. Okay, let's get back into it. So, so yeah, we've seen recent increases in area burned in the Western US. And then if we look towards the future, there's been a few studies showing that extreme fire weather frequency that can drive really large, these are weather conditions that can drive really large wildfires. We can see that extreme fire weather frequency is expected to continue to increase into the future. This figure from a paper a couple of years ago showed that the signal of extreme fire weather frequency is expected to emerge above the natural historic variability by 2080 in many parts of the world. So the goal of my current research is to understand how forced climate variability forced changes in climate variability and forced changes in the mean state are driving these changes or increases in extreme fire weather. So we've updated the data set that we're using. We're now using the CESM2 large ensemble, all 100 members, and looking at 1980 to 2100 in the late historic and SSB 37 simulations. And for all 100 members, we calculate the Canadian Forest Fire Weather Index. This is an index that takes daily climate inputs, maximum temperature, precipitation, relative humidity, and wind speed. And then we calculate 3 different moisture codes that represent drought conditions on different timescales. Oops, sorry. Daily to monthly timescales, and then we also then calculate 2 indices, and then finally get the Forest Fire Weather Index. And this index, basically, we have a daily value, and that tells us how likely a fire is to spread and how large that fire could possibly get. So one thing that we've been experimenting with is figuring out how to calculate an extreme threshold based on this fire weather index. So traditionally, or in recent studies, people use a fixed threshold. So this is based on the historic distribution. So in our case, it's 1980 to 2014. And we use a percentile value. So in our case, the 99th percentile, but it could be anywhere from the 90th to the 99.9th percentile. But basically, we find this threshold, we take this value, which is around 62, and we say anything above that is an extreme fire weather event. Another way you could define this threshold is by using a moving window distribution. So instead of just using a fixed threshold, we take a fixed distribution, we take we allow this threshold to change depending on the time that we're assessing. So for example, if we're assessing 2045 to 2079, we would now use this blue threshold instead. So, and you can see that it's a higher threshold because of changes in our climate. And lastly, maybe one that you haven't seen before is using this hybrid threshold. So this hybrid threshold allows the mean state to change. So it allows this P50 to change over time using the moving window distribution, but it does not allow the variability to change. So we instead impose the difference between the 99th percentile and the median in the historic period on top of the median of the moving window distribution. So you can see that this is slightly higher than the fixed threshold, but lower than the moving threshold for a future climate change scenario. So trying to simplify it a little bit, what the fixed threshold gives us is no forced changes in the mean and variability of that threshold. The moving one gives us a forced changes in the mean and variability. So we now have a threshold that represents those forced changes. And the hybrid threshold gives us only forced changes in the mean. So we've allowed the mean to change, but not the variability. So going back to our extreme fire weather events, so we also wanted to kind of capture extreme fire weather events more holistically. So these events are connected in space and time, so we wanted to capture that as well. So what we do is for each of these thresholds, we then identify grid points that exceed that threshold throughout all our ensemble members and throughout the whole analysis period. And we find grid points that are connected in space and time. So this is an example of one of these events. The shading is the fire weather index on a given day. So these are 6 consecutive days. And the circles here represent grid points that are spatiotemporally connected to each other. So you can see how this event evolves in time and over the region. And so for each threshold, we then have around 13,000 extreme fire weather events. And today I'll just focus on California, though we've looked at a lot of the Western US. And each of these events has an area, a duration, location, and then you can get all sorts of variables from it as well. I've also calculated the fire weather index, the maximum index and the average index as well. So now let's see how these characteristics are changing over time. So here again, I'm focusing on California for the summer months only. And on the top, I have the duration of events and the number of days. And on the bottom, I have the area of these events, so the total coverage over their lifetimes. And each, I'm showing here the result that you get by using these different thresholds. So you can see that with the moving threshold, you have virtually no change in the duration of your events or the area of your events. So this, by allowing the extreme threshold to change in time and follow changes in the mean and the variability, we see no changes in these events. However, when we use the fixed and hybrid thresholds, we see that events are on average 10 days longer and covered around 20 times the area they would have compared to the historic period. And I also forgot to mention that the spread here, so the median across ensembles is shown in the thick lines, and the 25th to 75th quantiles of the ensemble are shown in the shading. So we wanted to break down we wanted to isolate the changes in the mean and the variability. So to do that, we started to play around with these different results from these different thresholds. So first we looked at the fixed minus moving thresholds. This gives us the force changes in the mean and variability. And if we take the moving threshold away from the hybrid threshold, this gives us the force changes in the mean. And when we take the fixed minus hybrid results, this gives us the force changes in the variability. So I've taken the differences here for both the duration and area. And now let's bring our little cheat sheet back of what all this means. So if we look at this fixed minus moving, these force changes in the mean and variability, we find that that has the largest effect. So you can see this red line over time increases, and this effect is always larger than the two other effects. And this is because it represents the force changes in both the mean and the variability. If we look at the hybrid minus moving in this teal color, we see that this has the second largest effect. And so this shows us that the force changes in the mean are quite large as well. However, if we look at the force changes in just the variability, this has a really small effect over time, and this effect doesn't really change throughout the simulation period. So this is basically very preliminary results, and we're trying to continue to understand these different effects. And so I'll stop here and take any questions.
Great, thank you. Any questions for Danielle? Yep, Christine? Oh, wait a second. We need to wait for the green, the mics.
Yeah. Okay, I can't tell like what I'm looking at. Hi, Danielle, that was awesome. Can you tell me how you defined your variability for the hybrid? Was it just the standard deviation, or like, can you just expand on that a little?
Sure. Can you see the screen, the slide that I'm selecting now? Oh, this one. Better. Do you see that or no?
Yeah, we can see it.
Okay, cool. Sorry, I didn't hear you.
Oh, sorry.
So yeah, so it's so the way we do it is we take the median of the moving window distribution. So for example, let's say our moving window is this 2045 to 2079, and which is in blue. So we take the median of that, and then we impose, simply add on the difference between the median of the historic and the P99 of the historic. So this is kind of a really artificial way of, and very simple way of saying, okay, the tails, the distance between the median and the tails isn't changing over time, but the median is changing. So that's kind of our, the way we're thinking about it. But I'd be really happy to hear if you've done something different, or if you have any ideas or suggestions. Did that make sense?
Okay, I have to wait for the green light, I guess, and I figured out there.
Oh, okay.
No, I haven't really thought about it that deeply in this sort of context, but yeah, we can chat later.
Yeah, sounds great. Thanks, Christine.
Okay, thanks. Well, I'm going to set up Suchin's slides. I guess I had a question though, Danielle. Have you looked into kind of the relative roles of precipitation and atmospheric moisture and winds and things?
Yeah, so that's my next step. We're planning to recalculate these events by keeping each of the variables constant, or at the historic levels. So yeah, that's my next step, and I was hoping to have results for that for this presentation, but no such luck. So, but yeah, I'll share those with you, Isla, when I get those results.
Sounds good. Thanks.
Cool. Thanks.
Yeah, if you could stop sharing, then we'll
yeah,
bring.
I need to do that. Yeah. Okay.
Okay. Or do we want to enter full screen maybe? Okay, so our next speaker is Suchin, talking about amplified warming over tropical land. So yeah, if you put the mic on and switch that switched.
Hello, everyone. I'm Suqing. I'm a postdoc at UCLA working with Karen Ayla. And today I'm going to talk about our work on understanding the two perspectives on amplified warming over tropical land. So first, what is amplified warming over tropical land? Here we see two maps. The first one shows the summertime mean warming relative to the global mean. And the second one shows warming in the hot tail relative to the local mean. So for the mean warming, we see land warms more than ocean, and dry land warms more than moist land. And for the tail warming, we see that across almost all the tropical land, the extreme hot days were more than the mean, were more than the average days. And there are two main perspectives on understanding this phenomena. The first one is based on atmospheric dynamics. So the idea is taken changes in moist static energy as a constraint total, and it partitions between a warming component and a moistening component. So based on a weak temperature gradient and a convective quasi-equilibrium, it can be derived that the moist static energy increase in the boundary layer is uniform across land and ocean. And there is a moisture constraint, which assumes that the moistening over land is a fraction of that over ocean. And because it moistens less over land, so land warms more. This perspective was first applied to understand the mean land-ocean warming contrast, but it is recently applied to understand the variability as well. And the second perspective is from the surface. So it focuses on the partition of the net radiation received by the land's surface into sensible heat versus latent heat. And so the argument emphasizes that when soil dries or plants' physiology changes, latent heat decreases and surface flux partitions towards sensible heat. And therefore, warming in the near surface is amplified. And so we aim to compare the two perspectives and ask how they are connected. And we first want to compare a full spatial temporal distribution of the key variables in the two perspectives. And before we do that, I want to bring a note that land is very complicated. So first, there is temporal variability. And so when on the right-hand side here, you see this is one example grid cell from the Southern Africa in one model. So this shows the relationship between latent heat and soil moisture. The left is colored by precipitation, right is colored by temperature. And when soil is dry, when it is on the dry days, latent heat is low, and then it increases with increase of soil moisture. And then at some point, latent heat loses sensitivity to soil moisture, and then it decreases during the rainy days. And so the stage where latent heat sensitivity increase with soil moisture is called the transitional regime. And in this regime, drying of the soil moisture will feed back onto the temperature and warms the temperature. And second, beyond the temporal variability, so the spatially land is very heterogeneous. So this map shows the percentile of the climatological aridity index. We have places like the desert, which has a very high aridity, and we have places like Amazon or like Central Africa, which is very moist. And the latent heat soil moisture relationship is quite different across different regions. And also for a certain geological location, different models represent the relationship differently. So a newer version of the GFDL model shows a different shape, and CESM2 shows a different shape. and also other models. But an effective way to examine the spatial temporal distribution is through this phase space. Because so if we just not carefully just simply average things across a time period or across regions, or like aggregate all data together, it's easier to lose the important signals. But by organizing data into this kind of phase space, so for this kind of phase space, the x-axis is formed by the daily soil moisture percentile. So along the axis, we're looking at local dry days to local wet days. And y-axis is formed by the percentile of the climatological aridity index. So along the y-axis, we're looking at moist region to dry region. And back to the two perspectives. We can plot the changes in a key variable in this phase space. And along the black curve, we're looking at the transitional regime where latent heat is sensitive to soil moisture. And so for moist static energy increase, we see that so for the moist conditions, the increase of MSE is uniform, which is consistent with the original theory. And but over dry regions and on dry days, the increase is smaller. And so the uniform MSE assumption breaks down. And therefore, we find that it's hard to provide an accurate prediction for temperature increase for these conditions based on that theory. So this includes places like desert. And in fact, and the reason is because in those conditions, the MSE is not, it is too dry, so MSE is not high enough to reach the convective threshold. But in fact, those conditions are the conditions that warm the most. But despite that, we see a general partition between warming and moistening. So on dry days and over dry places, it moistens less and warms more. And for the surface perspective, we do see this strong partition between the sensible and latent heat, especially in the transitional regime. And one interesting note is that we might also expect that sensible heat increases over the desert, but we do not see it here. And the short and dirty answer is that surface long wave, upwelling long wave radiation is partly playing a role for sensible heat. So to compare the two, the atmospheric perspective provides a general principle on the TQ partition, but it is not explicitly coupled to the surface. And the surface perspective is process-based. We know the physical process, but it is local and is not coupled to the broader atmospheric dynamics. But through comparing the full spatial temporal distribution, we see that there is a general correspondence of the two perspectives, especially for the conditions in the transitional regime. And we do note that there is a discrepancy in terms of moistening. So in those conditions, latent heat decreases, so evapotranspiration decreases, but the atmospheric humidity is increasing. Despite that, it is increasing less than other conditions, but it is increasing. So this is because the atmospheric Q has other source and sinks beyond evapotranspiration, such as the large-scale convergence and the formation of condensation into condensates. And a note for relative humidity. So relative humidity is often taken as an indicator for atmospheric dryness, but it depends on both Q and T. So here we see relative humidity strongly decreases in these in the transition regime in correspondence to the soil moisture drying and the latent heat decrease. But the decrease of the relative humidity here is strongly affected by the temperature feedback. And next, we ask, so which one is more important, is more strongly associated with a strong warming, whether it's climatological dryness or changes in dryness? So in the atmospheric perspective, in their moisture constraint, the gamma, this ratio that tells us that land moistens less, is determined by the base climate state only. So we do not need land to get drier to have land warm more. But in the surface perspective, it emphasizes that soil dries and the flux partition changes. And to investigate this, we define a partition factor psi that represents the, to connect the temperature component to the total. So the inverse of that is represent the ratio of the temperature component to the total for both perspectives. And for a climate change, we decompose the change in the total into a component that keeps the base partition and a component that has changes in partition. And we reorganize the equation, and we relate we can relate the magnitude of warming to one is changes in total, which is the analog for the forcing in the climate sensitivity studies, and a term that is a sensitivity which is decided by the base climate dryness, and another term that reflects contribution from changes in partition. So the idea is, given a certain changes in total, how base climate dryness and changes in dryness will affect the magnitude of warming. And here, the y-axis is the warming magnitude, x-axis is the base climate sensitivity. The color is the changes in partition, and each dot is 1 pixel in the phase space that you've seen before. So we see a general relationship between the warming magnitude and base climate sensitivity. So a place that is drier in the base climate will warm more. And beyond this general quasi-linear relationship, in the intermediate conditions between wet and dry, the changes in partition further enhances or dampens the warming for a given base climate sensitivity. So for the atmospheric perspective, we see a similar shape. But one thing different is, so for the color, the atmospheric perspective, it always partitions towards moistening, while the surface perspective, so in the intermediate conditions, some conditions partition towards sensible, and others partition towards latent. And to summarize, so the two perspectives show a general correspondence, which indicates that the atmospheric perspective carries strong surface information, and there is a discrepancy in moistening, which results from other sources and sinks in the atmospheric humidity besides evapotranspiration. And we show that the base climate dryness can largely explain the magnitude of warming. And beyond that, during the intermediate conditions between wet and dry, the changes in partition further enhances or dampens the warming. After this, I will work with Karen Ayla on using CESM2 to run simulations and see how important is land surface for the warming magnitude. That's all. Thank you.
Any questions for Susan?
Just a quick clarification question. Is the base state or base climate dryness calculated for the mean day or the hot days?
Yes, this is a good question. It is calculated across, considering the variability. So that's it's based on the phase space. So the base climate dryness can have a spatial temporal distribution. So it's not averaged over the time.
Okay, you calculate like every time and then.
Yes. Here it is that, but that is another way of doing it. We can also do it in that way. But here I keep the temporal variability.
Any other questions? Yeah, Rob?
Well, also, I guess just a bit of a clarification, but this psi that you defined, you had it defined in different ways for the two different perspectives. Is it the same quantity then, or oh, you have different scripts for it, okay. So it is a different quantity, but it's trying to quantify the role of the partitioning in each theory?
Yes.
Okay.
Okay, thank you very much. All right, moving on to our final talk in this session, which is a remote talk from Haruki Hirasawa. So I'll stop sharing here. Haruki, are you able to share your screen?
Hold on. Should... Okay, oh. No, I'm having some permissions issues. So actually, if you could share from over there, that'd be great.
Does it, are you fine with me sharing it here and advancing the slides?
Yeah, that's fine.
Okay. Okay.
Okay, yeah. Thank you. So my name is Haruki. I'm a postdoc at the University of Victoria in Victoria, Canada. And today I'll be discussing some work that we have been doing with our collaborators at the Palo Alto Research Center and the University of Washington, where we're looking at using an AI implementation of the fluctuation dissipation theorem in order to project climate responses to radiation anomalies. Next slide, please. So the fluctuation dissipation theorem is a theorem that comes out of statistical mechanics. And put simply, it states that the response of certain dynamical systems can be estimated using the statistics of the internal fluctuations of the system. And it's been hypothesized that the climate is one such system where the FDT can be applied. And so there have been several attempts throughout the years to do this with varying degrees of success. And so, for example, here is one relatively nice example by Gritson and Brandstater, where they used the FDT to project the climate response in the community climate model 0 to heating anomalies in the atmosphere. Okay, next slide, please. So one common formulation of the FDT for climate purposes is in terms of a linear response function. So in these cases, the projected response, which I'm denoting delta y here, is estimated to be equal to the product of the linear response function L and the forcing vector delta F, where L is estimated from the covariance matrix of the internal variability of the climate system. And so this covariance matrix is calculated at a range of different time lags and then integrated over those time lags out to some point where it's assumed that the lag covariance essentially converges to noise. So next slide, please. So when we're applying FDT, there are several assumptions that need to be made. And for one, typically, especially for the climate, we need to do pretty substantial dimension reductions in order to be able to, properly calculate the covariance matrices. Another assumption made is that the statistics of the variables we're interested in are near Gaussian, and also that the responses that of the system are linear. And finally, because we need to calculate the covariance at pretty long time lags, we also need a large reference data set of internal variability in order to get a good estimate of that covariance matrix. And so what we wanted to do is see if we could loosen some of these requirements by replacing the classic linear response function with an AI response operator, and in particular, hoping to, reduce the amount of dimension reduction we need to do and loosen the assumptions on the Gaussian statistics. So next slide, please. So the AI model that we used, or rather our colleagues at Park created, is a spherical multi-layer perceptron model. And what it does is it emulates the it's a regression model that maps from monthly mean radiation anomalies. So here we're using cloud and cloud, shortwave, and longwave anomalies, as well as clear sky anomalies at the surface and top of atmosphere. And then it maps those anomalies in those variables to anomalies in selected output variables. So here we've chosen precipitation, surface temperature, and surface pressure. And one key thing we do is that we regrid our data to a spherical icosahedral grid, and this is to avoid dealing with grid area variations, which might complicate the implementation of the AI model. Next slide, please. So for our training data, we're using the CSM2 large ensemble, and this is because we do require the AI still requires a large amount of internal variability information to be properly trained. And so in this case, we're using data from the CSM2 smooth biomass burning historical simulations. So that's the second 50 ensemble members of the historical simulations. And in order to pre-process the data for training, what we do is we remove the ensemble mean at each grid point and each month in the time series, so that we only have the monthly time scale or month-to-month internal variability at a given at each of the grid points. And so, yeah, one key thing is that we are removing the seasonal cycle in our data here. Next slide, please. So, sorry, I'm not very good at explaining this part yet, but so we've essentially developed a sort of ad hoc method of applying FDT using the AI models we've trained. And so first off, what we do is we train the AI range, or essentially an array of different AI models at the different time lags. And then each of these AI models, as I said, are regression models. And essentially what they do is they map from the input field X of I, which is the radiation anomalies, to some, what I'm interpreting as the average of possible trajectories of the output variables Y for a given time lag tau. And so in order to project the climate response, we first run the model many times on different sampled input fields, X of I, and then we run them again with those same input fields, but perturbed with some radiation anomaly delta F. And then we average over the output, the difference of those two outputs for many different sampled input fields. And then we bring in our FDT idea again here and integrate over the range of different lag models that we've trained, where out to, in our case, 60 months, which is maybe too short for some of the processes that, slower ocean processes, but this is sort of our preliminary upper limit that we're using here. Next slide, please. Okay, so as a test case, what we're using marine cloud brightening. So marine cloud brightening is a proposed solar radiation geoengineering technology where sea salt aerosol is injected into marine boundary layer clouds to increase the albedo and cool the surface. And so what makes MCB interesting for our purposes is that there's a wide range of possible MCB forcing patterns, and it's not really practical to assess all the possible different forcing patterns using ESMs. And so we're sort of hoping that this sort of FDT method might be a tool that can be used to perform preliminary assessments of different intervention patterns. Next slide, please. In order to evaluate our model, we've taken some data from a separate project we're working on, where we've imposed marine cloud brightening in CSM2, in this case by setting cloud droplet number concentrations to 600 per centimeter cubed in 3 regions with that have a high concentration of clouds that are sensitive to cloud droplet number concentration perturbations. And so you can see them here in panel A and C, which are CRES, which is the cloud shortwave radiation anomalies. And so we're increasing CDNC in the subtropical Northeast Pacific, Southeast Pacific, and Southeast Atlantic. And then we obtain the radiation anomalies that we impose in our AI model from fixed SSD simulations in CSM2. And this is the delta F that we impose in our AI model. Next slide, please. Okay, so here I'm showing some results. So on the left, I'm showing the true response from CSM2 coupled simulations, the response of the coupled model to the MCB perturbations. And then on the right, I'm showing the projected anomalies that we get out of the AI model, integrated over the different time lags. And we see that so the AI model is actually doing a pretty good job in terms of projecting the pattern of the climate response to the marine cloud brightening interventions. But importantly, it is overestimating the magnitude of the response. But nevertheless, I think there's quite a few nice features that it seems like the AI model is properly capturing. For example, if you look at C and D, where we're showing the precipitation anomalies, you can see that the AI model is correctly projecting that MCB will increase rainfall over West Africa, South Asia, and Australia, but it's reducing precipitation over the Amazon and Southern North America. And these sort of patterns are being properly captured. So next slide, please. So I guess one thing to notice that in the previous slide, I'm showing quite a large perturbation, but if we switch to smaller, more regional perturbations, we start seeing some of the weaknesses of the AI method. So here I'm showing the temperature anomaly due to perturbations in each of the 3 regions that I mentioned before, the Northeast Pacific, Southeast Pacific, and Southeast Atlantic. And here we're seeing larger discrepancies between CSM2 and the AI, where we're getting, in particular for the Northeast Pacific, the AI model is projecting a stronger La Nina-like response. And so essentially it appears that the AI model is perhaps overweighting, and so when it's training. But there are indications that it's learning non-ENSO signals. So for example, in panels E and F, I'm showing the Southeast Atlantic response, and we're getting this Southeast Atlantic cooling and Amazon and tropical Pacific warming pattern that we also see in the CSM simulations. Next slide, please. Okay, so just to conclude, so we've developed an ad hoc method for implementing FDT using an AI model, and we do find that the large data pool provided by the CSM2 large ensemble is crucial for our AI model training. And applying FDT with this AI method is able to skillfully project the climate response pattern to marine cloud brightening, but it pretty substantially overestimates the magnitude of the response. So there's obviously more work to be done in order to improve the model, but I think there is a good indication that this sort of method could be a useful tool for generating first look estimates of climate responses to forcing, for example, for scenario development, whether it is for geoengineering or for other sorts of short-term climate forces scenarios. Thank you.
Thank you. Are there any questions for Haruki, either online or in the room? Yeah, Matt?
Do you need me to
No,
speak into
we have mics.
Okay.
When
Do you have any thoughts as to why it's overestimating the response?
Yeah, I mean, I have a couple different, I think, a couple different possible culprits. I think, for one, the method we're using is sort of, I think we do need to go back into the FDT theory and try to, if you recall that linear response operator, that there's the, well, first there's the covariance matrix at the different lags, but there's also that inverse of the autocovariance matrix. And so I think trying to figure out how that translates into the AI would, I think that might be, a key to fixing or at least reducing this magnitude issue.
Okay, well, thanks a lot. Thanks to all the speakers, and I apologize for all the technical difficulties. Hopefully things will go a bit smoother this afternoon. I guess there are a couple of things I want to say before we take a quick break. One is that we'll have a happy hour at 4:30. So Elizabeth sent out a sign-up sheet. If you could sign up, then we'd have some idea of the numbers so that we can, yep. Okay, okay, so for those online, if you didn't hear that, apparently this sign-up sheet is already expired, so we'll try and get that fixed, and we'll have a rough estimate. So feel free to join us at 4:30 at Under the Sun if you're around. The other thing was, yeah, for online speakers, you need to go to YouTube now for the seminar at 11. And then also any virtual speakers, I think it's probably a good idea if we check in before the session starts after lunch to just make sure you can share your screens. So I'll come back 15 minutes before the session so that we can try and get that sorted. All right, thanks a lot, and we'll see you at the seminar at 11.